recording.
In fact, as a continuation of that, I mean, now it's getting recorded, but I think it's okay. Like after a semester, I thought I should request again. And then I made the error that I wrote the email and then I wrote an email to inside the department that I hope this works this time. And that also meant I accidentally emailed, but I didn't write anything wrong or anything. It was a decent email. So they're nice. Okay, let's see. Oh, what's happening? Oh.
Because I know from watching these videos, a slightly higher resolution camera would benefit.
Okay.
And I know there was one video that I was watching that the lighting was off, like it was dark.
No, I agree.
Because I was looking at something, I was like, what am I seeing? Is there, it's almost like, was it overcast that day? Did one of the lights out?
But you did get a camera for yourself in your department, right? I think from what I heard.
Yes.
And
It is one of the benefits of being a smaller school who got COVID relief money.
God. No, I think it's important.
Mine's fixed though, so I just have a board about probably half this half and to that end, and it just shines on it. It doesn't change, so it's just. So if I step too far away from the board, then it's just a disembodied voice talking.
So this is the second last week of classes, and I did get a lot of homework submissions, but I haven't graded yet. So since you guys took some time, I can also take a little bit. And
Fair.
Hopefully I'll try to finish it off. It's occupying my table. So I would like to clear it off maybe this week. In this last 2 weeks, I will have one homework due. It's a standard homework that I give in this related to special relativity. If you have taken my E&M course, it will be very similar to that. I think it's exactly the same. So you will have it, but you still have to, sorry, still submit it, rewrite, I guess, or yeah, rewrite, and I don't know. Is that reasonable to say? I think you should. Sometimes the rewriting doesn't matter. And the final exam will have a problem. I think I talked about if you drop a particle straight, it is half AD square, z is equal to half AD square. But if you were to drop it horizontally, that is a parabolic form. It takes the curve is parabolic. We would like to know if it is relativistic, what kind of equations does it satisfy? So you will solve that, or I will break that problem down into many steps, and you work on that. So I had to write that problem. So those are the two problems we will discuss. So homework 11. So here is how it goes. So since I will be teaching this all the way for 2 weeks, so I'll make it due on Friday. And it's going to be optional. Oh, so that solves the problem of that. I think that's what I was thinking. But having set optional, it only means that if you don't want, you don't have to submit it. But the content is important. Like everything we do in it is so very relevant. Is that clear one? No, not yet. I haven't. It should not take too much, but I was thinking anyway, you won't be able to begin it today based on whatever I'm going to teach. It's not going to be there. So that's why I took the liberty to build it. I'll probably post it by the evening. Goodbye. Final exam. Yeah, this is to be posted, right? So to be posted. Probably by very soon, whenever I get a chance. Final exam is May 6th, Friday, 10:15. And there will be at least small component of the exam which will be due, which has to be done in class, probably exactly like midterm 2, and the major part of it will be take home.
When did we get the exam?
Oh yeah, this cannot be take home in the sense like midterm 2 where I gave the problem in the exam and then you went back and did it. This has to be before. If everything goes well, before Friday of next week, on before April 29th. Sufficiently in advance, at least 5 days in advance, if not a week in advance. Okay. I have to make that question. I have it on paper. I have to actually type it up. That's why I'm not promising which day. Okay. So we want to change gears here, and I'm going to do this very abruptly. We have been working with conserved quantities. We have been developing the Lagrangian, and ideally speaking, I should develop the operator quantity that discusses this special relativity where it is independent of the reference frame and then reach here. But I'm going to jump that because it will take me another week to develop that, and I've not done that before. So this sounds like it is completely independent, but it should be in principle connected. It should be connected with the ideas that we have already discussed. But historically speaking, it came from electrodynamics. It was, so what we're talking about is special theory of relativity. Let's begin by what it is. So how many of you have taken, have seen special relativity in some form or the other? Right. All of you have seen one of the suggestions in special relativity is that there is a maximum speed. And what's the maximum speed? Speed of light in vacuum, right? Because speed of light in medium can be slower than that. Why special? Why is it called special?
It's only for, no, it's only.
Correct. And not, yeah, the frames. Yeah. So the basic idea, and so that is this relativity principle. So what we are talking about here is that relativity principle, or principle of relativity, it's often called. And it says that physics should not care for what kind of coordinate system you use or how you measure it, like whether you measure it or I measure it, which lab you measure it, what instrument you use. Physics should not depend on that, or the physical, certain, or at least certain physical results should not depend on it. There will be quantities that will depend on the measurements. There should be a lot of conclusions. For example, we are born and we die, right? So there is a information content in there that should not change. Like you're born and then you die. It shouldn't happen then. In another measuring apparatus, someone else comes and sees the same thing happening, and they say, oh, first someone died and then they were born. That doesn't happen. Or that's an observation we make, or that's a law. In many ways, at a philosophical level, we say that everything we do has to obey that. And as of today, everything has happened like that. We do not see in any frame someone dying and then being born. It also has to do with the logical consistency with which we do physics. That is, A implies B and B implies C. That means A implies C. So there's a logical content in that, and that depends on that. So in that sense, whatever we are talking about is, we do not have any theories. Before Newton's law, if you want to say, before electrodynamic Maxwell's equations, before Newton's laws. So we don't have anything on the slate in a sense. It is just position and time. And we are describing what are we doing here. So one of the thing is that we want to write equations like Newton's laws. And one thing we assume is that these equations do not change in time. Right? Whether I'm now or tomorrow, my equations should remain the same. Right? At least that's an assumption. Right? You can always go back and assume that no, I'm not going to obey this, and come up with some conclusions. But everything we do as of now seems to be with the philosophy that I write an equation today, and 500 years later, it should be valid. I write an equation here, hopefully it should be valid in another galaxy. Does Newton's law change in another galaxy? Do you have to change your G? Probably not, and that's why we say it's a universal constant. It doesn't depend on position and time. So these kind of properties we pretty much assume, and that we want to quantize a little, make it a little more quantitative. And here what we say is that, so relativity principle, it's special in the sense we talk only about relative frames that are going with uniform velocity with each other. It can be made general. Then you say that, why should I make this restriction? Change the restriction from uniform velocity to any velocity, and that's general relativity. And that's much harder. There is much more information content we have to build for that. Here we will confine our attention to things going with uniform velocity. So what is it we are talking about? So there is a frame. There is a, let's say, Z prime, P prime. There is a time and position. You sit on this coordinate system and you use your position and time as Z prime and P prime. And there is another observer who uses Z and T as their coordinates. And this coordinate is moving with velocity V. And for convenience alone, let us say it is in the, everything is happening along a line. So it is. And both of them are observing some physics, right? Some physical. So this is physics. By physics, I mean there is some physical process happening. There was a child that was born, lives for 50 years and dies. That's an observation you make, let's say. But let's make this more concrete. Something is moving in a straight line. That, like someone being born and dying, that's complicated. Something is just moving with uniform velocity. That's we don't even want to bring in acceleration because that's that needs more information. So something is moving here. It's like 3 cars now. So there is one observer, another observer, third observer, and they are all moving with velocity v's. That's all we would like to do. And the first assumption we make is that this is linear transformations. Like these things are connected. So we would like to know what kind of transformations are z and t. So let's say z prime is equal to some a, and this can depend only on the velocity v times z plus b, which could be a velocity dependent, and times t, and t prime would be, I don't use c because c is going to be the speed of light. One can immediately ask, why did I choose this to be linear? Why did I choose this to be linear? And one can say that this is part of the a place where it is special relativity, or one could also motivate this very roughly saying that if your space is homogeneous and isotropic, then this is needed. For example, if I want the same equations to be true in another galaxy, I should be able to move my frame to somewhere else and get the same principles going. So I'm not going to show this, but you can say that this is motivated, but not necessarily easy, motivated by homogeneous and isotropic space. That means to say that my whatever I'm discussing here should be valid in another corner of the world, and it should be valid today or 1,000 years down the line. And this is linear approximation, or we're saying this is linear. So that's probably not very sufficient information to give, but it's a significant simplicity in there. So question this, since this is so basic level, so you want to really question what are the assumptions we are putting in when we assume those things. So it's going to be linear, and we are again observing something moving using 2 coordinates. One is z prime and one is z. And we would like to know what are the possibilities. Like what is the possibility of A, B, E, and V? One of the possibility is Galilean transformation. So just a rough knowledge of what's possible. One is Galilean transformation, and there you say that Z, what is Galilean transformation? Anyone? If this was Galilean transformation, what is your Z and T primes?
T prime is T.
T prime is T, good.
T prime is V T plus.
Z minus V, right? Or Z minus or plus, it depends on how you choose. Right? So that's your Galilean transformation. And there is also a possibility that there's Lorentz transformation, which is what is special relativity. What is Lorentz transformation? Have you guys heard of Lorentz transformation? Lorentz transformation? All of us have heard about it. So what is the equations? That's probably harder. Anyone remembers? So what is the prime? And it's also linear, which is what we are actually trying to derive here. And what is it? What does it look like? This looks very similar. So there's Z minus VT. And this is multiplied by gamma, where gamma is equal to 1 over 1 minus V squared over C squared. And there is another piece which is V over C squared times Z minus gamma beta times gamma. So that's the gamma. And then there is the gamma times T, which is, I think that's what it is. It seems like it is possible to have two such constructions, and you immediately ask, is there any other possibility? Right? Is there any other transformation you come across between for relative? Presuming principle of relativity, have you heard of any other transformation? You can have that as a quiz. Can you think of any other transformation other than Galilean transformation and Lorentz transformation? And we will show that, I mean, between these two, under what conditions do you get Galilean and what conditions Lorentz? Okay. So again, what are we trying to say here? So we start from, we have this as our transformation. We are observing this, and we would like to know what are the conditions we can put on A, B, E, and V. For that, we need to bring in and say that what do we expect, like what are we requiring. So let's first say that if something is at rest, let's say in Z prime, so if something is at rest at Z prime, so this is Z prime, T prime, and this is velocity V, and this is ZT. And that's your physics, right? There is some particle at rest at Z prime. And now we impose something. This is if you want like boundary conditions you're putting in. You have some differential equation. Then you say that at least I know this quantity very clearly. So we say that if something is at rest in the Z prime frame, I say that it should be Z prime is equal to 0. Right? And not only at rest, let's say it should be constant. I mean, it is at the origin of the Z prime. So then you make a requirement that then that should be the case. We require that at least with that much we understand that if you're in the rest frame, if I'm measuring my own position, I'm not moving. Right? If I take a ruler and measure my position forever, I will do the same thing if I'm measuring, going with uniform velocity. But what about Z? What are this coordinate measure? Let's call this primed and unprimed, right? Just for giving it a name. The prime coordinate, we'll see that you're going this way. So it seems like this person will be going backward. So this should be Z should come out to be equal to minus VT. That's what you expect. So you say that if someone is at rest in one of the frames, this is what the two should observe, that we require. Kind of. If that is the case, that puts some conditions on A, B, E, and F. If this is an observation, if this is a condition, then that implies I can put this in here. Z prime is 0. And that's equal to A of V. And times Z plus B of V and times T. Also, notice that this person is moving to the left, so I should also put in the minus V in there, right? So this is minus V. But Z is equal to minus VT. So Z, substitute that, so that Z is equal A of minus V times minus VT plus P of minus V times T. And that tells you that P of V, P of minus V is equal to V times A of minus V. I'll change V to minus V, and I learned that V, which is a function of V, is minus V times A. Just putting one condition, I learned all of that. So if I were to substitute this in here, I learn immediately that the conclusion is Z prime now is A, which is a function of V times Z minus VT. And T prime is still E of V, Z plus F of V times T. So remember, if you have your Lorentz transformations, you get that structure immediately, Z minus VT. And Z minus VT construction was there both in Galilean transformation and in Lorentz transformation. It seems to suggest that in Galilean transformation, your A is 1, and in your Lorentz transformation, A is your gamma, which is 1 over square root of 1 minus V square over C square. Okay, so that's one statement. And the second statement is that when we are measuring quantities, as now I can have a situation where this frame is going to the positive direction or negative direction. It is not really the inverse. Inverse will be when this frame is going with the negative V. That's what, or we will call it the inverse. At this point, I'm just going to change V to minus V and ask what's my equation. So let's consider the scenario. So let's do the same thing here. This is your frame here. This time, this is now going with velocity V. This is ZT, and this is Z prime. And that could be quantities that doesn't really depend on your V, whether you're approaching or not approaching. And under these conditions, we will require that A of V should be equal to A of V. So that's a, let me say at this point, I'm going to assume this. And then you ask what could be the implications if, so what could be the implication of this not being true? Okay, so I won't address that here. And since like the earlier point, I would put this as a quiz. So I am going to assume that this is true, that when the frame is coming towards you or going away from you, A changes. This velocity V does change sign, notice, but it's only A that does not change sign. Okay, and it will be that we should come up with a principle which says that, okay, this cannot be true. So for physical reasons, you require this, but offhand, I don't have any reason. Any reason you can think of why A of V should be the same as A of minus V? Something is coming towards you or going away from you, A should not change. But that's harder. We will leave that as a quiz. Think about it. Okay. So we are going to assume this A of minus V is A of plus. And this is third. And finally, one more actually, and then we will put in the two conditions. So it seems like a sufficient number of steps, but relatively simple. This is a transformation itself. You're saying that at rest something looks like this, something coming towards you, going away from you, as there's a form of the equations remain the same. And finally, now we say that a frame which is going this way, so that's Z prime, T prime. So this is going to be the important piece here. So that is an observation that is made. So that's a physics you make using this two coordinate system. And in another way you do this. So that's your V, that's your minus V. So whether your frame, one of the frame is going to the right, or whether the other frame is going to the left, there should be no difference. So this is called the reciprocal velocity. And under these two, the physics you see should be, equations should remain the same. So under these two equations, or transformation equations should remain the same. And same, and that's the word we often use, the word covariant. Covariant means it is not that the quantity itself as a numerical number remains the same, the equations remain the same. It's like saying Maxwell's equation in each reference frame remains the same, or Newton's law. We always say that in every inertial frame it looks the same. If you were not in an inertial frame, if you are in a non-inertial frame, you have to put in a pseudo first, but as far as you're in an inertial frame, Newton's law looks exactly the same. So what are we requiring in this case? So if you're here, we already know what it is. So it is Z prime is equal to A of V times Z minus VT. What about the other situation? What we say is that, and I've written only the first equation, but that will be sufficient. And the other equation will be Z is equal to A. I mean, this frame, I'm looking at Z prime, that's going to be exactly the same. So it is Z prime plus VT, this is minus V. So what is the connection between these two? How did I get one from the other? I changed Z and Z prime. I swapped Z and Z prime. I swapped T and T prime. And I moved from V to minus V. So the reciprocal velocity relation says that if I change my coordinates, z to z prime, t to t prime, and I put my velocity to be negative, then the equations should remain the same. That is, A should be exactly the same form in there. This is called the covariant form of your equations. It's like saying Newton's law remains the same under, oh, this has to be moved. Sorry. Okay, clear? So again, we have some linear transformations. We assume this is relatively straightforward. This one I did not motivate, and this is the important requirement we are making, which will actually give us the two Galilean and the Lorentz transformations. Until here, I haven't differentiated between whether I'm doing Lorentz transformation or Galilean transformation. Everything, both of them has to satisfy these relations. So we are saying that this four pieces together is what we will call principle of relativity. Right? So when I said here earlier relativity principle, these four steps is what we mean by principle of relativity. How things should look like when you are making an observation. Next, let's say this is going to be the next step is the only difference between the two. But before that, let me say, how do you get Galilean transformation, right? So let's get the Galilean transformation to begin with. So this is a digression. So we'll come back to that. So there is a fifth step, which is, what is the fifth step, by the way? That is principle of relativity. And there are two postulates of Einstein, right? One is principle of relativity, which I have broken into 4 steps, and speed of light is a constant, right? That is going to be the fifth step, and we will immediately. But now at this point, I'm making a digression because Galilean relativity doesn't need that constancy of speed of light, so I should be able to get that. So what does Galileo do? Implicitly, it assumes that t prime is equal to t, right? So you require that there is no difference between t prime and t. Basically, that immediately says that E is 0 and F is 1. So it immediately implies that E is equal to 0 and F is equal to 1 in my transformation. And what else can I do? I have things here, right? Yeah. So if I go back to this equation, so that is z prime is equal to a of z minus vt. Right, so that's fine. Equation, and z is equal to a times z prime plus v prime, right? That's my two equations here. Set t equal to t prime. So if I have t prime is equal to t, these two are the same. Then add these two equations. So I started from here, rewrote that. I set t prime equal to t and add them. And these two terms will cancel. One is minus, one is plus, that will cancel out. Here I have z prime plus z. And this is a times z plus z prime. And that's z plus 0, right? So this rest of the terms cancel out. And this implies immediately that a is equal to 1. Right? And that's Galilean relativity. So just by, if you set this equal to the same, then you have Galilean relativity. So what I mean to say is that until now, we haven't invoked special Einstein's relativity. That's the point I want to convey. These things or just principle of relativity requires these 4 steps. There is nothing as of now which has required Einstein's relativity. And now that means the 5th step is the most crucial one. So, question? Yeah.
Is function of B or minus B?
It doesn't matter, right? Because that was the point here. That's why I wanted that step before, right? And which I did not motivate. I don't have a very simple motivation for. So if this doesn't matter, that's why I didn't write that. So after this step, I don't have to specify V or minus V. Yeah, so it's the same. Okay. Okay. So A is equal to 1. Okay, so the digression gets is over now, and we come back to step 5, which is Einstein's speed of light. And what is the 5th equation? The point is there is at least one speed which seems to be the same for both observers. There is some effect. You can say, you don't even have to say it as a speed. There is at least some quantity which seems to be the same in both the observer. And what does that mean? That so there exists a speed which is same for both, both observers. What does that mean? So that means, what that means is that the first observer measures it as Z prime is equal to C times T. So this is the special speed. There exists a speed C. There's a special speed C for which the first observer measures Z prime is equal to CT and Z is equal to CT. Something special that everything, both the observers use the same equations to describe that. So that's the constancy of speed of light, if you want. Like the thought process is that if you have a flashlight and you're traveling in a car, what is the speed of that light measured by an observer sitting on the ground? Is it V plus C, the movement of the car? Does it add on to that or not? And the claim is that, or all experimental observation seems to suggest that no, it doesn't add up. And that was the reason. This was all motivated from electrodynamics. There was this Maxwell's equations came up, and there was a constancy of speed of light inbuilt in that. And there were experiments done to see that relative motion, and you didn't see it. And then you say that, okay, maybe that can be accommodated. Here, we are saying that there exists some speed of light. For example, you could ask speed of light comes from Maxwell's equation, correct? Maxwell's equation. The moment you write Maxwell's equation, you say that electric field oscillates like a wave, like an ocean wave is there. What is an ocean wave? There is an amplitude of water rising up and down, or particles in water are going up and down, but energy and momentum is going to the horizontally. Something is moving up and down vertically, but energy and momentum is going horizontally, right? That's the idea of the wave. You come and say in electrodynamics, you say that electric and magnetic field are oscillating up and down, but there is an energy going in the right side, and that's an electromagnetic wave. And it turns out that speed is C, right? Whatever we know as speed of light in vacuum. But then there is an entirely independent theory, which is called gravitational waves. It's Einstein's theory. That also has a wave, so think of a planet just oscillating. It is it's right increasing in size, then reducing in size, increasing in size, and reducing in size, and that will create a wave. That's what is called a gravitational wave. It should not be spherical. If it's a spherical particle, it doesn't do it. It has to have a quadrupole moment. It does not even a dipole moment does it. It has to have a quadrupole moment, and then you see a gravitational wave. And then you can ask the same question as to if there is a gravitational wave coming from another galaxy to our galaxy, with what speed is it coming? What is the speed of gravitational waves, by the way? To our knowledge?
Speed of light.
Speed of light. But now these are two different theories. You can ask, is it possible that you can have two speeds that come out the same? Right? Since these are two independent theories, you could ask, is it possible that there are two speeds that come out exactly the same for an observer? Okay. I'll leave that as an exercise for you. So can there be two speeds? Can there be two speeds that look exactly the same for different observers? That means to say, it doesn't have to, I cannot say speed of light unless it's speed of gravity. What tells you that gravitational wave and electromagnetic wave has exactly the speed of light? Can it be off in the 14th digit, which we cannot measure? 13th digit probably we can measure. 14th digit we cannot measure. Can it be off there? Is it possible? So is there a theoretical requirement, fundamental requirement that they should be the same? That's the, but that's a digression again. What Einstein said is that electromagnetic waves are moved at speed of light, but in this way of going, we are not even saying it has to be the electromagnetic wave. There exists a speed at this point C, where both the observer comes. So it's more at a philosophical level. We are not invoking electromagnetism as such. So this is just saying that that exists. If that is the case, put it back in here, right? These were our equations. Put it back in here and let's see what we learn out of that. So we say Z prime is equal to CT, right? So let's start with Z prime. So this is our requirement, and that means we start with Z prime is equal to A times Z minus VT. Substitute these two quantities, C T prime is equal to A times Z is C times T minus V times T. So C times T prime is equal to A times C minus V times T. Same thing, I have another equation. Z is equal to A times Z prime minus VT prime. Z is CT, A C times T prime minus V times T prime. So CT is equal to A times C minus V plus, plus. Thank you. Thank you. Thank you very much. Okay. They have to be the same. So maybe I can write one more line here. T prime over P is equal to A times C minus V over C. And T prime over P here is C over A times C plus V is equal to T prime over T. That's just a algebra, I put in steps in there. But if both has to be for consistency, we require that this should be the same, and that immediately gives you A times C minus V over C is equal to C over A times C plus V. So A squared is equal to C squared over C squared minus V squared, which implies that A is equal to 1 over 1 minus V squared or C squared. And once you have A, you can go back and get your E and V. Can we? Yeah, let's do that also. But before that, I want to stress, notice, all this was principle of relativity. Just requiring this, it seems to suggest that A is this, and seems to be the only solution at this point. So it seems to be, so whatever I was trying to tell, that, oh, is there another possibility? So that is not like earlier I asked, is there any other possibility, Canadian versus Lawrence? It seems like, so that's your quiz. Is there anything else possible in this? Is there any freedom you can put in between principle of relativity and the speed of light and get something else? It seems like there's not much freedom in there. But let's keep going. We have A now, we should get E and V, right? So let's get that. So let's take P prime is equal to E times Z plus F times T. And what can I do? How do I find this? So this here, so CT, and I have T prime minus T here. Yeah, let's see. So this is E is equal to C times T plus F times T, and that's T prime. And all this is for this phenomena that we are talking about, this particular speed of light. So this gives me, so that's T prime. So T prime over T is equal to E times C plus F. So T prime over T is A times that's nothing but A times C minus V over C. Doesn't have much. C minus V. Okay, let's go back. The unimportant ones, I'm stuck here. Okay. So we have A. Let's go back down here itself. At this point, we had Z prime is equal to 0 and Z is equal to minus VT. Maybe they'll do the same thing and that's good. Okay, again, T prime is equal to E times Z plus F times T. I can replace Z or I can replace T prime, or I can replace, I guess, is there anything else I can do? T, I can write as Z. C times T. Oh, maybe I can use the same idea here, right? So I can also say, this also means that T has to be equal to E times Z prime plus F times T prime, probably. And do the same thing, E times C times T prime, F times T prime. No. I'll mess up if I do something wrong. Okay. I'm not so too confident.
I think use the second one.
Second one, right? Probably.
Yeah, on the relation between F and E.
Can I find E here? Yeah, so let's see this. So you're saying I can put C equal to minus VT in here, right? Right? Yeah, probably. So I substituted this only here. So let's, yeah, good point. So let's me use this fact in this equation. So this is the box I'm creating. Okay, and T prime is equal to E times Z is minus VT. That's minus VT plus F times T. So that's equal to minus E times V plus F times T. Right. Yeah, but I don't learn much, right? Like this is very specific to this case, and I need a condition between E and F.
Can also say that the event start at Z prime equals 0 and T prime equals 0. You
Say that again?
can say that the event start at Z prime and T prime are at 0.
Oh, T prime is also 0? But then, no, that's not, we don't know, right? Because then you're fixing the time T prime. Because time evolves, right? When you're sitting here in the restaurant, time evolves. So T prime changes. We don't know how it changes, but T prime evolves linearly, maybe. Yeah, but we don't know whether it is linear or not linear. Yeah, so yeah, let's not impose that. It's straightforward. Something. It's bad. I'll come back. Okay. Oh, I've got quiz, right? Find E and F. And I do not, what is that? Okay. It's only 10 minutes, I'll give up. Try, because there are two more equations, right? I wrote only the Z prime. Maybe try that. So that is T prime is equal to E times C plus F times T. I'm trying to resist reusing this because I have not assumed anything with the V dependence in there. But if I were to do this, so this will be T will be E times Z prime plus F times T prime. But then I have to substitute V to minus V also. V minus. And I do know that E of V changes sign. So F of V is 1 over 1 minus B squared over C squared. But E of V has a velocity dependency. 1 minus B squared over C squared. So yeah, let me come back instead of confusing. There's a little. Okay, I don't want to give anything wrong.
How did you get F and E?
I have not got it. This is, I did not. That's the answer. Yeah, that's the answer. I did not detect it. Yes. I was trying to say that I started by saying, let me analyze this equation, but I cannot use it because I don't know how E and F transform under minus V. I did not assume that. Maybe I had assumed that, but then I recall being able to do, once I reached here, then it was straightforward, but I guess I got too overconfident with that, or I'm missing something trivial. But let me not mix up. So if you allow me, I'll get back to this. For now, it is almost anything that I cannot do, give it. Sorry. Yeah. That's all I do. Once we have the Lorentz transformation, we'll next time come and define the transformation. What are the implications? What are the immediate implications? Try to understand the geometry of the transformation. That's what we will do. It is compare it with rotations, and then pretty much do the whole of Newton's mechanics in this context. So we will redefine, then say redefine, we will define what is called for velocity, for acceleration, for force, for momentum, for what else? For, that's it, I guess. Yeah. And if possible, electric and magnetic field, but that will be a problem with the exam. So all that, we have 3 lectures, pretty quick. But everything goes smooth. Okay, thank you. I'm sorry about
Early on in the lecture, you're talking about the speed of light in a vacuum versus in a medium.
yes.
And I think we discussed it before, the Cherenkov radiation.
Yes.
And I actually got to witness.
Oh,
um,
that process?
This was at the University of Missouri, Columbia.
Columbia, yes, they have.
They have the, I
reactor.
kept asking people, why is the water down in that reactor so blue?
Blue.
And
It's a glacier.
nobody could answer the question
Huh.
until, well, because the grad students that they had giving the tours weren't physics majors. And so there was I finally said, let's assume that I have a degree in physics. Who could explain this to me? And they found the physicist on duty, and they explained it, because I'd never, I'd never heard of the idea of something traveling faster than the speed of light. And then I found out it's possible within a medium.
Correct. So what Rob is saying is that we typically make the statement that nothing can go faster than speed of light, but there is two more words you have to complete it. No, nothing can go faster than speed of light in vacuum. You can go faster than speed of light in a medium. In a medium, light is going slower, so something else can go faster than that. So there is some room between speed of light in vacuum and speed of light in the medium. So something else could come and go.
So in the medium, there is something.
Yeah, you can. It is, think of a fighter jet. When a fighter jet, like think of sound. Instead of light, for a moment, think of sound. And sound speed is 300 meters per second. That's where the vibrations go at that speed. And you can ask, how will things look like or sound like if you go faster than speed of sound? And fighter jets do all the time. Fighter jets go faster than speed of sound, and you will notice that fighter jets sound different. They come with a boom, like they go after it has gone. You know, before it has reached you, you probably will hear. How does that work? Go here, and then the boom comes. Yeah, it will go. Yeah, speed. Yeah, the fighter jet will cross you, and then you will hear the sound. Right, there is a delay between that, and it comes in a cone. All the light gets concentrated in a cone, and there is too much of energy there. That's why it breaks windows. If you, I lived next to this military bases, and windows can break if you're too close to the runway. And now the same thing can happen in light. Keep the same idea that speed of sound is now replaced with speed of light, but now this is in a medium, so it is slightly less. So instead of 3 into 10 raised to 8, it could be 2 into 10 raised to 8 meters per second. So there's room between 2 into 10 raised to 8 and 3 into 10 raised to 8. Something else can move at that speed. Right? So now think of a particle moving at 2.5 meters per 2.5 into 10 raised to 8 meters per second, and it is traveling faster than speed of light in that medium. And that's called Cherenkov radiation. It's observed all the time. It is used as a detector. And again, it has the same cone phenomena. All the energy comes on a cone. You can collect all the energy. And this radiation is like you have, why is the sky blue? This radiation, you can have a frequency dependence on this, and it is significantly concentrated on blue, and much more than your, actually much less than the sky. Sky goes as 1/4 power of frequency. I think this is only linear. Oh, but it is linear. That might be something that's just linear in frequency, but it's more on the blue, and that's the point. And so when you look into this detectors or a nuclear reactor typically has this detector, then all the water will be blue there, because there are particles that are significantly going faster than speed of light. I don't know. It went around all
They said
the
it was
places.
neutrons that were coming out of the chamber.
It's going faster. Yeah. So did I make sense?
Doesn't this affect the cause and effect?
Does it? Why do you say that? Tell me.
The causal effect.
Why would it have? It's like saying, like it's easy to say no, but it doesn't. But you're asking why. Why would it have?
Going faster than the speed of light.
Yeah, you can see yourself. Is that the point? In that medium. Like, yeah, I think your argument is the following, but I think if I understand it right. So you typically the argument with causality is that okay, you were born here, right? And light falls on you, right? And you go in here, so you walk, right? So this is you. So this is light. If you were to stand here, you will see yourself. But now, if I can go faster than light, I'll come and stand here and see myself back in there. And in this case, I guess it's homework. Good question. I don't know. It cannot. Okay. Here, a simple answer is that nothing can. Causality is too sacred. As far as I have understood, that's one of the very. If you break causality, many things go wrong. Physics goes wrong in a sense. So I have never seen causality being broken, other than very fancy theories where you are presuming, unless speculative theories, they always there is a chance that you can break. But causality is never broken. So, but I don't know how to argue that. So that's my point. It's given too much importance. A lot of things can go wrong there, but your point is correct. Oh, I know.
Yeah.
Like the photons themselves are still traveling at the speed of light, or like the speed of light in a vacuum.
In medium.
I think so, because the like I think, or this is how I thought it worked, is a photon, like at that scale, everything is still just empty space.
Oh, that's what you were saying.
So the photons are traveling at the same speed, but they just run into too many molecules along the way. So the information from the original event is still propagating at the same speed, but when you catch up, you're still seeing like delayed like light from that event, but the information is already dispersed.
Probably it's a good way of saying this. I would say, yeah, there is this very similar thing happening in Brillion's argument. So what happens is that if you have seen this refractive index, this is refractive index, and if you were to see a plot of this with frequency, it will look like this. And this is somewhere here is 1. Right? Refractive index has to be always greater than 1. And somewhere there is a region where it will go down below 1 and then come back. And right after relativity, this was a big issue. You say that, oh, things don't go far, things can go faster than light, or it's not causal here. And what Sommerfeld and Brilliant did, this is 1913, is that this is where the idea of a packet comes in. One component of light does go faster, but information as such is actually going slower than, so group velocity is always slower than light, but one particular frequency could be going faster. Maybe one has to invoke that, and that makes sense here because here there is a material property coming in. But I don't have a concrete answer to one. Right? So think about it. Make it a quiz. There's sufficient quizzes here, but this is after the class. So yeah, but good question, very good question. So I'll think of it if possible. But have Brilliant and Sommerfeld argument, maybe that should be a connection. I think that's what comes to my mind, and it is along the lines of what you is pointing out also. Maybe put it all together. Yeah, but good question. Okay, I should stop. Yeah, thank you. I'm sorry about not being able to teach. Enjoy. Okay.